everyone. My name is Arbaz Vimani. I'm a tutor here at the QLab for the Thomas Rivera Center. We're located at the second floor of the JPL. Today I'll be talking about General Chemistry 2. The specific topic is reaction rates. And so in this example question, you're given a reaction and then you're given experimental data on that reaction. So the rate of each of the reactants, and then the concentration of each of the reactants, and then the initial rate that comes from those conditions. So I'm going to start off by labeling condition 1, condition 2, and condition 3. And these were the 3 different reactions that occurred. So this question is asking first of all for the rate law and then the value of the rate constant. So in order to do that, first you have to start with the general template of the rate law, which is going to be rate equals the concentration of reactant A to the X times reactant B to the Y. And so we're going to use this template and apply our scenario to it. So rate, I actually forgot the constant K. That's very important. So rate equals the K constant times the concentration of the first reactant, which in our case is NO, and it's going to be raised to the X power, times the concentration of the second one, Cl2, raised to the Y. So the important thing to note here is that the exponents of the reactants do not correlate with the coefficients that are seen in the overall balanced reaction. So for rate law, you cannot use the overall balanced reaction to determine the exponents of the rate law. You have to be given experimental data in order to figure that out. And so what you do is you take ratios of the conditions in order to cross out things that stay the same and then solve for the ones that don't change. So an example is in these 3 conditions, if you have a scenario where 2 of the reactant concentrations stay the same, but the other 2 change, then we can manipulate that to cross out one of the exponents and solve for the other one. And so that's what we'll do. We'll take a ratio of condition 3 over 2. And so here you'll have a fraction, and on the numerator and denominator of the fraction, you're going to have the rate law for each condition. And so if it's 3 over 2, it's going to be the rate, which is 1.45 equals the rate constant times the 0.20 for NO raised to the X multiplied by 0.20 for Cl2 raised to the Y divided by 0.36, the rate of the second condition, equals the rate constant times 0.10 raised to the X multiplied by 0.20 raised to the Y. And so in this case, we see how the rate constant cancels out, and also the whole Cl2 concentration along with the exponents. And so as a result of this, what we get is we go ahead and divide all the terms. So 1.45 divided by 0.36 will give you 4.027 equals 0.2 divided by 0.1 equals 2 to the X power, and then the other stuff got cancelled. So in this case, in this case, you can kind of just see that X would have to equal 2 for this algebraic statement to be true. But for more complicated examples, the method you could use that would always work is to go ahead and take the log base 10 of both sides, because what this would do is it would go ahead and bring the exponent out as a product. So what it would be the log of 4.2027 equals x times the log of 2. So now to solve for x, it would be the log of 4.2027 divided by the log of 2. In this case, x equals 2. So now that we have x, we just need to solve for y. So now we have to look for a condition in which the x's cancel, but the y's don't. So we'll take a ratio of 2 over 1. So 0.36 to rate equals k times 0.1 to the x, and in this case we have the x, so we can just plug into for the x. The y is 0.20 divided by 0.18 equals the rate constant, 0.10 to the 2 power times 0.10 to the y. So the rate constants cancel, and the NO concentrations cancel. And so what we get for this ratio, 0.36 divided by 0.18 is 2 equals 0.2 divided by 0.1 is 2 to the y. So this case is very simple. Log of 2 equals y times the log of 2. So y will equal log of 2 divided by log 2, which is just 1. So now we have the exponents x and y. So what part A wants you to do is write the general template, but with the x's and the y's plugged in. And so in this case, it was a coincidence that the exponents of the rate law were the same as the coefficients, but that will not always be the case. So it's always important to do this process to figure out the actual exponents of the rate law. And so now part B asks for the rate constant. So since now we have the exponents, the concentrations, and the rate for each condition, the only thing that's unknown now is the k constant. So we can just use any one of the conditions, plug in all of our known values, and then just solve for the rate constant. And so that's exactly what we'll do. And I'll actually do it down here to give us a little bit more space. So let's just use condition 1 as an example. So 0.18 the rate equals, and this time let's go ahead and use our actual units, because then it'll also help us figure out the units for the rate constant. And so the units for the rate is molarity over time, or moles over liters times minute. So we'll go ahead and put that. So the rate equals the k constant times the concentration of NO, which is 0.10 moles over liters, raised to the second power, and that comes from our rate law there, multiplied by 0.10 and Cl2's concentration raised to the first power. So now if you were to go ahead and work this out, the left side would still be 0.18 moles over liters times minutes. The right side would be K, and we're going to go ahead and distribute the exponent. So it would be 0.1 to the second power, which is 0.01, and the square gets distributed not only to the 0.10 but also to the units as well. So it would be mole squared over liter squared. it's multiplied by 0.10 moles over liters. So 0.18 moles over liters times minute, that's K, and then 0.01 times 0.1 is equal to 0.001, and the moles squared gets combined with the moles to give moles to the third, and the liters squared gets combined with liters to the first to give liters to the third. Now the last step to isolate the K constant is to divide on both sides by the 0.001 moles cube over liters cube. So the actual number part here is pretty straightforward. It's just 0.18 divided by 0.001, which gives 180 as the numerical answer. But for the units, what you're essentially doing is you're doing moles over liters times minutes divided by moles to the third over liters to the third. And so this can be thought of as dividing two fractions, which is the same thing as multiplying by the reciprocal. So it's multiplied by liters to the third over moles to the third. So as we can see here, the liters cancel to give liters squared on the top, and the moles cancel to give moles to the second power on the denominator. So these are our units here for the K constant. It's liters squared on the top over moles to the squared. So this has been the question for reaction rates. Thanks for watching. Be sure to like us on Facebook and subscribe to our YouTube channel. If you have any more questions, remember to visit us at the QLab. We're located on the second floor of the JPL. Our hours of operation are Monday through Thursday from 10 to 8, Friday from 10 to 4, and Sunday from 12 to 7. Thank you.